I'm happy to have or to introduce Dr. Joris Libal. Great to have you, Joris. Joris is, as I mentioned, managing technology transfer at ISC Konstanz. Those of you who don't know ISC Konstanz, it's one of a number of European solar research institutes, and they are really standing out these days because they really focus on a lot of technologies that are currently being implemented by manufacturers around the world. I think Joris will probably also mention that. And I'm very much looking forward to your presentation. Joris, the floor is yours.
Hello, thank you, Michael, for the nice introduction. And yeah, it's a pleasure that we have the opportunity here to present our view on the current status. So let me check if this works. It's fine. Can you see my screen, full screen?
Yep.
Okay, perfect. Yeah, so good morning and good afternoon, everybody. So the title of the talk is Pushing PERC to Its Limits, and we will talk about the status and potential of industrial PERC technology. So at the beginning, I will start to say some words about ISC Konstanz. We'll look back to the switch from aluminum BSF to PERC and have some discussions when we talk about cell efficiencies and limits to see what the champion cell announcements versus the industrial reality mean. Then look at the status and the potential of the industrial PERC technology and have an outlook of about what comes after PERC. So ISC Konstanz is a non-profit association in Germany, has been founded in 2005. We are a team of 60 employees, most of them scientists, and coming from 20 different nations. We are focusing on R&D on crystalline silicon solar cells, modules and systems, and working with institutes and industrial partners in various types of projects. And an important focus, as already Michael mentioned, is we're doing technology transfer of PERC, Topcon, and N-type IBC. So this is the technologies we are focusing on the cell level. And today the topic is PERC. So looking back, the PERC has stepped in when the aluminum BSF came to its efficiency limit a little bit below 20% or around 20%. But in order to become viable for mass production, it has been necessary to develop an aluminum oxide deposition equipment, which is low cost and high yield. And at the same way, there was a need of monocrystalline Tucholsky wafers at a low cost, which has been strongly pushed by LONGi at those times. And also it was necessary to have an adapted aluminum paste, so which was able to create a void-free selective aluminum BSF. And this happened at around 2015, 2016, and nowadays PERC has become mainstream. So this is a standard process flow today and the PERC architecture. So on the front side, we just have this firing through silver fingers. And on the rear side, we have the passivation with the aluminum oxide and the local firing through aluminum back surface field. The sequence is very simple for the PERC today. We have the texture and cleaning, we're followed by the emitter diffusion. The laser doped selective emitter is nowadays standard in industry. It is followed by the chemical isolation and the low temperature thermal oxidation. Then we have on the rear side an aluminum oxide silicon nitride layer, which can be created by PCVD or ALD. On the front side, we have the PCVD silicon nitride passivation and reflective coating, followed by the screen printing metallization with silver and aluminum fast firing and IV measurement and sorting. So if we want to talk now about what is limit efficiencies, we have to put them also in the right perspective. And this is sometimes difficult. If we look at announcement in 2019, there was already announcement of a Longdi of 24% PERC cell. We have the Topcon cell by Jinko with 25.4%, heterojunctions above 26%. And last year there was even a PERC module with 23% efficiency. But if we have a closer look, the picture becomes clearer. So for example, the PERC cell, 24% had passivated contacts on the front side, which is not an industrial mature process today. It might come in the future, but it's not the real PERC cell, what most people think about. The Topcon cell, normally Topcon, which is now in industry, has passivated contacts on the rear side. This 25.4% cell had passivated contacts also on the front side. Another topic is measurements, even in CAL labs. Often we have grid resistance neglecting measurements, which lead to high fill factors. We'll come back to this also. And yeah, in the 23% PERC module, did consider only the active area, so only was referred to the area of the cells within the module only, not the standard efficiency of modules. So we wrote some paper, Radovan and me in the PV International, where we were talking about this topic last December. And in this context, we think that currently, even if record cell efficiencies are around 24% in industry, now PERC is between 22.5 and 23.5% cell efficiency. And module efficiencies, this is meanwhile higher, as we see later on. We get up to 21.5 even. And important point, we think the VOC is, without going to passivated contacts, is limited to 685 millivolts as an average. So to summarize this little discussion, in order to appreciate the champion cell announcements or press releases, so to be able to do an apple-to-apple comparison when we make a judgment about technologies, we should check the following points. So is the actual claimed cell architecture really what we think or what is claimed? So PERC cells, when they have front contacts, it's not what is a standard PERC cell, so it's more complex, more costly. Are all process steps that are used for manufacturing this champion cell, are they industrially viable? It means, are they cost effective? And then looking at the measurement of this record cell, has it been done in a calibration lab? And if yes, we have to look at the fine print. So if we have a fill factor due to grid resistance neglecting, which is over 85%, then this cannot be transferred to the module when interconnecting the cells. So that means if we base our considerations on this type of measurement, we will have a very high cell to module PMPP loss. So having this said, we think PERC is around up to 23% in industry. Topcon is something around 23.5% or approaching the 24%. And heterojunction is also up to 24%. The low-cost IBC Zebra is around 23.5 to 23.8% based on the above assumptions. And for PERC, now the state of the art is M10 wafer format, often with 10 bus bars, but there's a strong trend to G12 with 12 bus bars. And some typical IV parameters are listed here. We think this VOC can be around 685 millivolts, and with a current of 40.6 milliamps per square centimeter, fill factor of around 82%, we end up with 22.8 average cell efficiency, which is typical. It can be better for some manufacturers, but I think this is a typical value. If we now look at some possibilities to push this efficiency further, so there is a continuous optimization of the metallization ongoing. Also with G12, there are other grid designs, of course. and thereby we can further reduce the shaded and metallized area on the front side, which reduces the recombination on the metal contacts, and also the series resistance means we can increase the VOC, JSC, and fill factor with this measure. We can further improve the emitter doping profile and mostly the selective emitter paths. This also again gives another possibility of improving a little bit the VOC. Maybe some fine-tuning on texturization quality and anti-reflective coating will get a better JSC, better current. And overall, we can narrow the distribution of the IV parameters by getting more and more homogeneous and higher wafer quality, and also by improved statistical process control and the implementation of machine learning, so Industry 4.0 methods. And thereby we can decrease the number of low efficiency cells and increasing the average efficiency. And if we go further this path, we think the average efficiency of the average IV parameters can be expected to be reached in mass production would be a maximum VOC with this architecture that we presented before. So the standard PERC of 690 millivolt, the JSC up to 41 milliamps per square centimeter, and a fill factor of 82.5%. So we would end up with 23.3% average cell efficiency, which we think could be some limit, maybe slightly higher, but then PERC reached its efficiency limit. So I'm always talking about mass production and low-cost mass production and average cell efficiencies, of course. If we have a short look at the module efficiency that have been reported by TaiyangNews this February, we see that the mainstream PERC, there are many producers having modules with an efficiency of around 21.6%, and the best one from Longyi here is 21.7%. So we see here some small potential to go to with the module efficiencies towards 22%. So to summarize, even if this PERC cell efficiency seems to be close to its limit now, something like 23.3, 23.5% maybe, there's still continued progress made in the field of cost reduction. And so that means the equipment suppliers are developing machines with a higher and higher throughput, which is leading to lower CapEx expenses and lower chemicals consumptions per cell, and also lower footprint per throughput, and which is leading to reduced facility cost. Of course, everybody is continuing to work on reduced silver consumptions. And as mentioned before, this quality control, process control, and Industry 4.0 methods will lead also to increase of the process yield, which of course is also a very important cost factor. If you now look what comes after PERC, it is nice to have a look at the graph from Martin Hermle from Fraunhofer ISE, which divides the cell technology families in different efficiency ranges. And from our point of view, it's also interesting to see these efficiency ranges sorted by highest VOC that can be reached. So as mentioned before, without using passivated contact, so with the standard PERC architecture, the VOC will remain visibly below 700 millivolts. So the next step, next evolution step after PERC would be to implement passivated contacts on the rear side, because there we can do it homogeneously, because it's a light absorbing layer. And this will mean to switch to Topcon, which has passivated contacts on the rear side, and there it will be possible to exceed VOCs of 700 millivolts. So we would be in this range. And as a next evolutionary step after Topcon, we will have both polarities passivated. So this could be either a Topcon IBC cell where we have both contacts and on the rear side, or it could be what we internally at IC call a selfie cell. This would be also N-type cell, both-sided contacted and passivated contacts on both sides. Therefore, a selective polysilicon deposition or polysilicon passivation on the front side has to be developed. So the switch from, we had a look at the switch from aluminum BSF to PERC, and now we will be in a similar situation for Topcon. We think the switch from PERC to Topcon will come as soon as there is a mainstream and low-cost, high-yield deposition technology for the polysilicon. Nowadays, we have LPCVD as the mainstream, but there is options that are currently developed and introduced to industry that seem to be more interesting from cost and yield perspective. So PCVD, LPC, and PVD. But up to now, it's not yet clear who will be the winner there. There is a need of further reducing the cost gap between N and P-type wafers. And of course, N-type technologies need to reduce their silver consumption in order to become more competitive. Here's just a short glance on some cost of ownership calculations that we did internally. It is an example of a 5 gigawatt peak per year factory located in Asia. The wafer cost is a very low cost. Today we don't have this. This was the lowest cost beginning of last year, but we hope that in the future we can get back there when polysilicon prices will go down. Silver cost is around $700 per kilogram for this scenario, and as a result, we see that the Topcon cell today is around $0.02 per watt peak more costly than PERC. Of course, due to the high efficiency, higher module power, the cost gap will be lower on module level. And there are some installation scenarios depending on climate and also the type of PV system, where the Topcon is already competitive on LCV level. Just as an outlook in the future, we did some simulations of the advantage we have on the left side the losses and the recombinations for the Topcon cell with the passivated contacts only on the rear side, and compared this to the losses, the improved and reduced losses of the selfie cell that has passivated contacts also on the front side. And there we can see the main improvement is in the achievable VOC, which is going from 700 to 720 millivolts. And that means we have an efficiency potential of this cell, which is yes, visibly up above 24%, 24.5%, we can go there. And similarly, we can push then the passivated contacts on the rear side, and this will result in a Topcon IBC cell, which has even other advantages like a higher current due to lower front side shading. So as a summary, as we saw before, even if the bifacial PERC is coming to its efficiency limits, the cost reduction potential is still there. So there is still a cost gap to Topcon, and the bifacial PERC will improve further. So we think it will remain mainstream for some years still. And as soon as the polysilicon deposition is standardized and the silver consumption will be reduced for the Topcon, then the N-type technologies will take over. And as mentioned before, we think the next natural step is to introduce as it's already being done in industry, to introduce the passivated contacts on the rear side, which means to go to Topcon and to be able to have efficiencies up to 24%, average cell efficiencies in mass production. And later on, we think that the next step will be having the Topcon IBC with passivated contacts, both on the rear side. Okay, thank you very much for your attention.
Thanks, Joris. Great overview. And I think it was also important that you showed actually how sometimes that's sometimes not an apple-to-apple comparison is taking place when companies are publishing efficiencies. I think that's great also that you referred, maybe if just in case not everyone knows, at Taiyang what we are doing is, so every 1 month we check basically the websites of all big manufacturers to see and check their commercial modules. And then we publish this ranking. Joris has shown me always do that at the beginning of each month. And the idea is really only to look at commercial products, and we only take those companies that first have their spec sheet published on their website, so to make sure that it is really a commercial technology. And then what we also do is, because we realized when we were scanning it, that some module manufacturers that were module only manufacturers had higher efficiencies than companies that are integrated. So we found that a little bit strange. So what we also decided then is that we really go for mostly integrated companies, so that they only use their own cells to simply make sure this is somewhat or as transparent as it can be. If there are any questions to Joris, please type it into the chat. Joris is, I think, with us for some more time and will be happy to answer. Okay, thanks again for this great presentation.